Assalamualaikum warahmatullahi wabarakatuh. We are from Group 4. We'll be present about lab report experiment 5, which is stability of floating body. So this is the team member for this group, Nadia, Diana, and Adlan. Introduction. The stability of a body that floats on the surface of a liquid, such as a ship, is an obvious important. The head of the gravity determines whether the equilibrium is stable, neutral, or unstable. In this experiment, the stability of a pontoon may be assessed with its center of gravity at various heights. A comparison with calculated stability may also be made. Next, the objective for this experiment is first to determine the head of metal center, GM, using the tilting method. Second, to verify and understand the concept behind the stability of a simple floating body affected by the metacentric stage MG. Next, the scope. In this experiment, the distance between the base of the pontoon to the center of buoyancy, D, the distance by which the horizontal weight is moved, X, the pontoon's center of gravity, CG, the angle of tilt measure, theta, are used in this experiment to compute the metacenter. The metacenter is determined using several tilting and gravity center. The metacentric height must be positive for the floating body to remain stable. At the center of gravity rise, stability, restoring force, increase. Finally, the relative error percentage must be determined after conducting this experiment.
So, for the theory and working principle of this experiment for stability of the floating body, it is governed by the principles of buoyancy and the metacentric principle. The height of the metacenter, which is GM, is crucial for determining the stability of the floating body. A higher metacentric height indicates a greater initial stability against overturning. In this experiment, the stability of a pontoon is determined with the center of gravity at different heights of vertical weight. If a horizontal weight is moved with a distant x from the center, the pontoon will tilt, and the angle of tilt can be measured by using the plumb bob. The diagram besides shows its center of gravity G and its metacenter M. The distance between G and M is called metacentric height. When the object is still, the angle is introduced as shown in figure 4.0. X is the distance of the adjusted mass to center of gravity. B is the center of buoyancy, and G is the center of gravity. So in this experiment, we used to have two expressions for calculating the GM, which is the first one is GM equals to IO over V minus CG, and the second one is GM equals to WX over W, capital W, multiplied by time theta. And for this experiment, the tilt angle of the pontoon is determined using a plumb bob. The weight's horizontal displacement from the pontoon's equilibrium position, which is to the right or to the left, affects the tilt angle. So GM can be calculated as follows for an equilibrium system, which is using equation 4.2. In equation 4.2, GM indicates the metacentric height, W is indicated for horizontal weight, X is horizontal displacement, big W is equals to weight of whole set of pontoon body, and angle is the angle of tilt. Besides, we also can calculate the theoretical values and compare it with the experimental data. The following are the expression for a pontoon's area of the moment, which is we have equation 4.3 are the equation for BM is equals to I over V. I is the second moment of the water surface area at the vertical axis, and V is the volume of water displaced. Equation 4.4 is I equals to LB to the power of 3 over 12, which is L is the length of pontoon and B is the width of pontoon. We also have equation 4.5, which is we can use it to calculate the volume of water displaced, which is V equals to W over rho. W is the weight of the whole pontoon set of a whole pontoon body, and density is the density of water, which is the liquid that we use in this experiment. And lastly, we have equation 4.6, which is GM equals to BM minus BG, also equals to BM minus Y plus B over 2. Y is indicate the center of gravity, and B is the depth of water submersion in this experiment. So that's all for the theory and working principle.
So next, for the apparatus, there will have a ruler for the measurement, and then a pillar that will be attached with the horizontal weight, and have the vertical weight attached with the mass and also thread, and then have the pontoon stabilizer that will be used to find the CG, which is the center of gravity, and also have pontoon body and also the water tank. So now for the experimental setup, we assemble all the equipment and attach into each other, like in this figure 5.1. So now for the experimental setup for finding the center of gravity, we will put the pontoon body on the pontoon stabilizer. Next, for the methodology, first we measure the weight of the horizontal weight and the whole set of the pontoon body as shown in figure 5.0. Then we stabilize the pontoon mass using the pontoon stabilizer as shown in figure 5.2 with the vertical weight on top of the mass. The reading for the center of gravity we measured and record into the table as shown on the table 7.1. Then we position the horizontal weight along the mass and place the vertical weight on top of the mass as shown in figure 5.1. And then fill in the sink with water and floated the pontoon. Then for the next step, we check the zero datum between thread and scale before start the measurement. And then we move the horizontal weight from center to the right with the 10 mm at first, and then continue with 20 mm increment. We take note the angular displacement and record the data into the table result. And then we repeat the step 6 until 8 regarding to the changes of horizontal weight from center to the left with same increment. After then the part of the vertical weight on the top, we repeat step 2 until 9 for the changes of height of the vertical weight to the middle and the bottom of the mass. And then record all the angular displacement readings, value of CG, which is center of gravity, and D, which is height the pontoon mass that into the water. Then we record into the table result. Lastly, we calculate the metacentric height, which is GM, using the formula given in the table.
So for the result, we can see in figure 8.0, it shows the raw data collected from the experiment. we can see that when we adjust the vertical weight at the top, we can have a higher center of gravity and vice versa. Also, the depth of water submersion decreases with the center of gravity. The tilt of angle also for the both left and right movement decreasing in the reading for angle as the center of gravity becomes. Figure 8.0 is the raw data collected from the experiment without the calculated value of GM. And next, we have to calculate the metacentric height, GM, using the equation 4.2. As shown in this slide, GM is equals to Wx over W tangent angle. So we have W with the value of 0.293 multiplied by 10, which is the displacement to the right, and divided by capital W, which is the total mass of puntun, and also multiplied by tangent angle, which is we use 4 in this slide for the example of calculation. And then we need to repeat the same calculation for the 3 set of data with 3 different center of gravity, where the CG for top is 16 meter and depth is 29 millimeter. And for the middle, we have CG is equals to 33 millimeter and D is equals to 28.5 millimeter. And lastly, for the bottom, we have CG is equals to 15 millimeter and D is equals to 28.3 millimeter. We need to calculate all this, and the results as shown in figure 8.1 is the completed data for GM and GM for test 1, test 2, and test 3.
For the discussion, first we plot the graph of GM versus theta and determine the value of GM from the plotted graph when theta equals to 0. For the test 1, we adjust the vertical weight on top of the mass. And then we get the center of gravity equals to 16 millimeters, and then D equals to 29 millimeters. The angle of tail with the positive one, we adjust the horizontal weight from center to the right, while the negative one adjust the horizontal weight from center to the left. And then we calculate the metacentric height using the formula. We plot the graph GM versus theta, and then when theta equals to 0, the GM we get equals to 29 millimeters. From the graph, we can conclude that when theta equals to 0, the value of metacentric height GM is for test 1, which is top on the mass, GM equals to 29 millimeters, test 2, middle, GM equals to 49 millimeters, and lastly, test 3, bottom, GM equals to 59 millimeters. This graph means that the lower the place of the vertical weight on the mass, the higher of the metacentric height. This experiment on floating bodies relate to stability through Archimedes' principle, which states objects float when the buoyant force equals their weight. Stability is enhanced when the center of gravity is below the center of buoyancy. Measuring how far the object can tilt before tipping helps assess its stability. This concept applies to real-world scenarios like ship design.
So for the discussion 9.2, we need to calculate the value of GM for each test using an area of segment equation. So we also need to compare and discuss the value obtained with the GM from 9.1. So the first thing that we need to do is to use the equation 4.3, 4.4, 4.5, and 4.6 as shown in this slide. So we have some constant value, which is B, width of puntun we have 200 millimeter, we have L, length of puntun 350 millimeter, we have capital W, which is 1.56 kilogram, and also density of water, which is 1000 kg per meter cubic. So we just need to insert the value in the equation. I equals to LB to the power of 3 over 12, and also the equation B equals to W over density. And lastly, we need to insert the value of I and V in the GM equations, and we have the value of GM. This example of calculation is using the value of test 1, where the CG is equals to 16 and the D is equals to 29. We need to repeat the same calculation for test 2 and test 3 with different CG and D. The discussion continued by comparing the GM for theoretical value and the experimental value. As you can see in the table 9.2.1, the GM for each test have a large percentage error. For test 1, the percentage error is 71.92. For test 2, we have 41.55, and for test 3, we calculate the percentage error, which is 60.12. There are a few reasons that might influence the percentage inaccuracy estimated. One of the issues is parallax error. The reader's eye may not be perpendicular to the reading scale. This experiment used two mediums, which are air and water. So, to obtain the depth measurement, it may make the reader more difficult to read due to the light refraction. Furthermore, the puntun itself is unstable since it floats on the water. This might be caused by the air or wind flow in the area, which could have an influence on the puntun stability when floating in water. Furthermore, the issue might be produced by a random fault by the reader itself. To reduce the percentage error, students can turn off the fan to prevent the wind from interfering the puntun stabilization procedure. After that, students also should wait for the puntun to reach equilibrium, which occurs when it is stable, before taking the reading. Finally, each test should be taken 2 or 3 times reading, and the average data from the readings should be computed to achieve the highest level of data accuracy.
So the next part of discussion is discuss the reliance of the metal center on the position of the center of gravity in terms of stability of floating body. Based on the observation and the collected and processed data, the stability of the floating body can be used to characterize the reliance of the metal center on the location of the center of gravity. The floating body, which is the puntun, is more stable when the horizontal weight is moving away from the center of P equal to 0. Since the center of gravity, which is represented by the vertical weight, is at a lower point, the fact that test 3 tilted angle, which has a lower vertical weight, only slightly deviate from the first 2 tests, serve as evidence of this. This is because the metacentric height increases when the center of gravity lowers. The floating object is more stable the farther its center of gravity is from its metacenter. This is demonstrated by the value we obtain from the test result, which shows that in comparison to the result of test 1 and 2, test 3's GM value is the highest. Conversely, when the vertical weight is at greater point and the horizontal weight move away from the center, the bottom become less stable. The shifted angle of the thread, which is caused by the horizontal weight displacement, provide proof of this. The angle is inclined at the higher value in test 1. Additionally, the larger the horizontal weight movement, the greater the tilted angle. This occur because of the head of the GM will decrease as the center of gravity rise. As a result, the GM increase with lower center of gravity CG and decrease with the greater CG. Greater initial stability against overturning is implied by bigger metacentric height. The bottom will be in a stable position when the metacenter is above gravity and the GM value is positive, but an unstable position when the metacenter is below gravity and the GM value is negative. Therefore, it may be said that the floating body is more stable at the lower the CG and the larger the GM. The distance between the metacenter MC and the center of gravity CG is referred to as metacenter height GM, and as a result, it is significantly dependent on the CG. This indicates that anytime the CG shifts in relation to its initial position, due to the fact that the GM, which has been modified, quantified the separation between the MC and CG, the formula GM equal to BM minus BG can be used to get GM. Therefore, the value of BG will rise and subsequently lower the value of GM, or vice versa. When CG change higher than its starting point, regardless of the tilting angle, the floating can remain stable as long as the position above the floating body. Next, 9.4, discuss the effect of variation in angle of tilt on the position of the metacenter. The tilt angle affects where the metacenter is located. Furthermore, the position of the metacenter affects the tilt angle, while the horizontal weight is moving. This is because when a body undergoes an angular displacement, the center of buoyancy rotates and point in the direction of the tilt. Here, the buoyancy force and body weight create a righting or restoring coupling that rotate the body back to its starting point. This is also demonstrated by the equation Gm equal Ws over W tan theta. When the metacentric height decline, the angle of tilt increase and the center of gravity increase. Hence, a new center of buoyancy will form because of the shifted horizontal weight, and a new metacenter position will also be found. The result of the experiment demonstrates that neither the length nor the depth of a bottom submerged in water affect where the center of gravity CG is. In contrast, the weight of the bottom will shift where the CG is located according to Archimedes' principle, which states that when a structure is submerged in water, a certain amount of water is displaced. In the conclusion, the stability of buoyancy experiment illustrates the concept of stability and buoyancy by placing a floating object in a water container and attempting to keep it in an equilibrium position. The stability of the float is determined by the metacentric height Gm, which represents the distance between the center of gravity G and the metacenter M. A positive Gm indicates a stable body, as buoyancy restores stability when the bottom tilts. On the other hand, a negative Gm indicates that the aircraft is unstable and prone to capsizing. The position of the metacenter changes as the tilt angle changes and is proportional to the tilt angle as indicated by the equation Gm equal to Ws over W tan theta. We are able to deduce from the experiment that a suspended object is more stable the higher its metacentric height. Additionally, the inclination angle rises from zero, but the lift center shift and the metacenter's height varies in the relation to the lift line of actions intersection. As a result, the study of metacentric is crucial for assessing the stability of and resilience of artificial buoy design.